Imagine standing on a quiet hill, watching the sky burst into a symphony of colours as the sun peaks above the horizon. It's a daily spectacle that many of us take for granted. The warm hues of orange, red and pink splashing across the sky. Yet, this beautiful sunrise is only the final chapter in the light's long journey. If we trace the path of these photons from their endpoint in the retina at the back of your eye, through the Earth's atmosphere, across the 150 million kilometer void separating our planet from its host star, and finally through the varied and tumultuous layers of that star, we discover the source of the warmth on your face and the colors painted across the sky. The sun's core, a nuclear engine that has been raging for 4.5 billion years. Born in a cosmic nursery from the remnants of ancient stars, the glowing sphere of searing plasma that dominates our sky is the product of complex forces that have played out over millennia. So let's take a journey back in time, tracing the origins of the sun, exploring its intricate layers, and mapping the elements that make up its very structure. I'm Alex McColgan, and you're watching Astrum. Join me as we dive into the depths of our sun and learn what secrets lie behind the blinding curtain of light and time. To understand how the sun formed, we must go back to before our solar system even existed, about 4.6 billion years ago. At that time, in a relatively quiet region of the Milky Way galaxy, a massive cloud of gas and dust, known as a giant molecular cloud, drifted silently through space. This was no ordinary cloud. It was immense, possibly spanning hundreds of light years across, with a mass equivalent to millions of suns. Within this cloud lay the scattered remnants of ancient stars that had long since exhausted their nuclear fuel and exploded as supernovae, casting their enriched contents into the cosmos. This stellar debris included a mix of elements such as hydrogen and helium, the building blocks of stars, along with heavier elements like carbon, oxygen, nitrogen, and iron. The presence of these elements made this molecular cloud fertile ground for forming new stars and planetary systems. However, such a massive cloud requires a trigger to initiate the cascading collapse that results in stellar birth. Scientists believe that this trigger could have been a shockwave from a nearby supernova explosion that compressed parts of the cloud, causing it to fragment and collapse into regions of higher density. This collapse marked the beginning of the pre-solar nebula, the dense region within the molecular cloud that would eventually give birth to our solar system. Some scientists have even proposed a name for this hypothetical exploding star, Coatlicue. Named after the Aztec goddess of earth and fertility, Coatlicue symbolizes the death and rebirth cycle, where in this case, the death of one star can seed the formation of new ones. As the gravitational collapse of the giant molecular cloud progressed, it did not result in a single massive object, but rather fragmented into multiple dense clumps. This fragmentation occurs due to a phenomenon known as Jeans instability, named after the British physicist Sir James Jeans. The Jeans length is a critical distance within a cloud at which the forces of gravity are balanced with the natural internal gas pressure that keeps the cloud propped up. When a defined section of the cloud exceeds the Jeans length, it will collapse in on itself. Different regions within the molecular cloud exceed this Jeans length at different times due to variations in density and temperature. As these regions become gravitationally unstable, they collapse independently to form multiple protostellar cores as opposed to one single massive body. The protostellar core was the earliest phase in our sun's life that was recognizably star-like, crunching itself into a tighter and tighter sphere by the ever-clenching fist of its own gravity. The core is surrounded by infalling gas and dust. As more material accumulates, the core becomes denser and hotter, setting the stage for the next phase of star formation, the protostar. Once a protostellar core becomes sufficiently dense and hot, It evolves into a protostar. The central region has heated up to the point that it begins to emit light and heat from the energy released by gravitational contraction. But its core has yet to reach the temperatures required to ignite nuclear fusion in the core. As the protostar continues to accumulate material and grow in mass, the pressure and temperature in its core increase dramatically. Our Sun developed through this embryonic state of contraction and heating for millions of years, before eventually building up its core temperature to about 10 million degrees Celsius, at which point hydrogen nuclei began to fuse into helium. And with that, the Sun was born. At this stage, the innate angular momentum of the surrounding material that shrouds the infant star generates rotation. A cloud of this size will always have some slight rotation, nothing in the universe is still, and conservation of angular momentum dictates that the cloud must spin faster and faster as it crunches down into tighter space, similar to how a spinning figure skater speeds up as they tuck in their arms. Around the equator of rotation, some of the material is moving fast enough to stay in orbit, but higher up and lower down, the momentum is insufficient to resist the protostar's ravenous pull and falls helplessly into its jaws. And so, the cloud flattens out into a disk, a protoplanetary disk. This disk is a cosmic lottery. As it cools and coalesces, planets, moons, asteroids, and comets will be relentlessly created and destroyed. Some material will be robbed of its momentum and tumble into the Sun, while neighboring matter will go on to become part of the many bodies that make up our solar system today. With its new ability to fuse hydrogen atoms into helium, the Sun could finally generate energy to push back against the forces of gravity that sought to squeeze it further. The energy streaming out of the fusion reactions created an outward radiation pressure that balanced the inward gravitational pull of the gas, allowing the young star to achieve a stable state known as hydrostatic equilibrium. In this state, the star no longer contracts under its own gravity, and it enters a stable phase of its life known as the main sequence. This balancing act between internal pressure pushing outward and gravity crushing in is the axis that defines every stage of the Sun and all stars' lives. We saw it during the initial collapse, and here as it settles into a stable main sequence star, and it will be the pendulum that eventually swings towards its dramatic death. For now, let's unpick the process of nuclear fusion and how it's capable of keeping an object as massive as the Sun stable and steady for billions of years. To understand how nuclear fusion occurs in the Sun, we need to examine extreme conditions present within its core. Today, temperatures reach around 15 million degrees Celsius and pressures more than 250 billion times that of the Earth's atmosphere. In this blazing cauldron, hydrogen atoms are stripped of their electrons, forming a plasma composed of free protons and electrons. Under such intense conditions, these protons, normally repelled by their shared positive electric charges, are forced into extremely close proximity. The force that usually keeps them apart is the Coulomb force, an electrostatic repulsion between positively charged particles. It's exactly the same force that resists as you try to push the same ends of a bar magnet together. Overcoming this force is the primary challenge for nuclear fusion to occur. Despite the extreme kinetic energy of protons in the Sun's core, most collisions are still not energetic enough to overcome the Coulomb barrier. Under normal conditions, protons need immense energy to get close enough for the strong nuclear force to bind them together. This barrier is so significant that physicists around the early 1920s, using a classical understanding of how particles interact with each other, determined that fusion should not occur at the temperatures and pressures found in the Sun's core. To solve the puzzle, we needed a scientific model that has come to explain many of the seemingly impossible phenomena we observe in the universe: quantum mechanics. The quantum mechanics revolution of the 1920s introduced the concept of particles behaving both as particles and as waves. One of these phenomena is quantum tunneling, where particles have a certain probability of tunneling through a barrier even when they lack the classical energy needed to overcome it. In the Sun's core, quantum tunneling allows a small fraction of protons to effectively bypass the Coulomb barrier without having to climb over it in the classical sense. Even though these protons do not have enough kinetic energy to overcome the electrostatic repulsion directly, quantum mechanics gives them a chance to appear on the other side of the barrier. To visualize this process, consider a diagram of the Coulomb barrier. In the diagram, you will see a high energy barrier representing the repulsive electrostatic force between two protons at varying distances. The energy needed to climb over this barrier is represented as a peak. The calculations of a classical physicist would require the Sun to have temperatures high in the billions of degrees Celsius, thousands and thousands of times higher than the Sun's core, to hurdle this barrier. But quantum mechanics allows for the probability wave of a proton to tunnel through this barrier, appearing on the other side without ever going over the peak. This tunneling effect is what enables fusion to occur in stars like the Sun, despite the seemingly insurmountable Coulomb barrier. Once a proton has tunneled through the Coulomb barrier, it gets close enough to another proton for the strong nuclear force to take over. The strong nuclear force, which is far more powerful than the Coulomb force, operates only at very short ranges, on the order of femtometers, where 1 femtometer is equal to 10 to the power minus 15 meters, roughly the size of a single proton. The strong nuclear force binds the protons together, but this is only the first step in a series of nuclear events known as the proton-proton chain. The proton-proton chain reaction is the dominant fusion pathway in the Sun and other stars of similar size, accounting for roughly 99% of the Sun's energy production. It starts with two free-roaming protons combining to form deuterium, a heavy isotope of hydrogen, along with the emission of a positron and a neutrino. This step is rare but essential, as it allows the fusion process to continue. The deuterium then rapidly fuses with another proton to form helium-3, releasing a high-energy photon, a gamma ray. In the final step, two helium-3 nuclei collide and fuse to form helium-4, releasing two protons and a significant amount of energy in the form of radiation. While the proton-proton chain is the dominant fusion process in the Sun, there is another pathway at play, particularly in stars hotter and more massive than our Sun. This pathway is known as the CNO cycle, short for carbon, nitrogen, oxygen. In this cycle, carbon, nitrogen and oxygen nuclei act as catalysts to fuse protons into helium. The CNO cycle is more efficient at higher temperatures and only contributes a small percentage of our Sun's energy output. The energy produced in these fusion reactions comes from a small amount of mass being converted into energy, as described by Einstein's famous equation E equals mc squared. In the fusion process, the mass of the resulting helium-4 nucleus is slightly less than the combined mass of the original 4 protons. This missing mass is not lost, but rather converted into energy that radiates outward from the Sun. Every second, the Sun converts about 4.3 million tons of its mass into energy. That's right, the Sun is losing mass all the time. To put this into perspective, this is the equivalent of the mass of about 3 million cars being turned into pure energy every second. This is the energy that ultimately powers the Sun and provides the light and heat that reaches Earth. But before these photons pouring out of these reactions can reach the Earth and everything else in the solar system and beyond, they must first escape the 700,000 kilometers of chaotic solar interior that lies above them. To truly grasp the complexity of the Sun and its stratified layers, let's follow a single photon, a particle of light, from its creation within a proton-proton reaction all the way to the surface. This journey is anything but straightforward. In fact, it will take thousands, if not hundreds of thousands of years for this photon to complete its journey, passing through several distinct layers of the Sun, each with their own unique properties and behaviors. As we've already found out, our photon's journey starts in the core, a region that spans about 25% of the Sun's radius, but holds nearly half of its total mass. And, as we've also heard, the core is incredibly dense. At around 160 grams per cubic centimeter, it's over 20 times denser than iron. To put that into perspective, if your phone was made of material that dense, it would weigh as much as a heavy-duty sledgehammer. For our photon, this means that the environment is so tightly packed with particles, it cannot travel far before being absorbed by a neighboring particle. Of course, not long later, that particle will pack the photon's bags and send it out into the melee of the core for another particle to catch and release in some other random direction. It's a bit like trying to navigate through a dense crowd, where every few steps you bump into someone and have to change direction. This constant interaction of absorption and re-emission is what gives the core its chaotic nature, resulting in a journey for a photon that is more of a random walk than a direct path outward. This random movement of photons is reminiscent of Brownian motion, where particles suspended in a fluid move erratically due to collisions with smaller, fast-moving molecules. And there is no preference for the direction that a photon could fly back out of a particle that had just absorbed it. In theory, a photon could make it all the way to the surface of the Sun before random chance directs it back towards the core. To add to the complexity, as photons are continuously absorbed and re-emitted, the energy gradually decreases from gamma rays to X-rays and eventually to visible light as they move towards the Sun's outer layers. Understanding the processes occurring within the Sun's core has been a challenging endeavor for astronomers. The core is completely obscured by the outer layers of the Sun, meaning we cannot directly observe it through any form of light. Instead, scientists have developed ingenious methods to infer the dynamics of the roaring inferno below. One of the key techniques is the study of helioseismology, the observation of waves rippling across the Sun's surface. Just like seismologists study earthquakes to understand Earth's interior, helioseismologists measure the vibrations of the Sun's surface caused by sound waves that travel through its interior. These sound waves are influenced by the temperature, density, and composition of the Sun's layers, allowing scientists to construct models of what is happening deep within. Solar neutrinos, elusive subatomic particles that I've talked about in a previous video, are also released during the fusion reactions in the Sun's core. Neutrinos interact so weakly with matter that they can travel straight out of the Sun in just 2 seconds, hardly aware of the tangle their photon counterparts are caught up in. For decades, solar neutrino detectors on Earth measured fewer neutrinos than predicted by theoretical models, leading to what was known as the solar neutrino problem. It wasn't until scientists discovered that neutrinos change their properties, or flavors, on their journey to Earth, that the mystery was resolved, confirming both our understanding of particle physics and the nuclear processes in the Sun's core. Next, the photon enters the radiative zone, which extends from the edge of the core to about 70% of the Sun's radius. Here, temperatures gradually drop from 15 million degrees to around 2 million degrees Celsius. The density of matter also drops, going from around the density of gold in the zone's depths to less than water near the top. The dominant energy transportation method is still this frenetic process of photons skittering through the layer, carrying their energy on average towards the surface. And as the density of the plasma continues to decrease as we move outward, our photon has slightly more wiggle room, capable of bigger leaps between interactions. But even here, outside of the core, the Sun's material is still so opaque that even a few centimeters could block out as much light as hundreds of meters of water. We are able to envision such precise models of the Sun's interior because of models like the Standard Solar Model, or SSM. It is a mathematical framework based on the principles of hydrostatic equilibrium, energy conservation, and radiative transfer. Essentially using our understanding of how materials and fluids behave here in our laboratories on Earth to infer the properties of a place out of our reach. The SSM models how energy is passed between particles in its complex equations, describing how photons are transported through the dense plasma. This allows us to calculate how transparent the solar material is to radiation at different temperatures and densities, and from there we can work out where the radiative zone ends and the next layer begins. This is one of my favorite things about mathematics. It allows us to explore environments that we can never visit, almost like how quantum tunneling allows protons to jump over the Coulomb barrier and produce the photons we are now following. As our photon approaches the upper boundary of the radiative zone, it enters the tachocline, a thin, transitional layer where the radiative zone meets the next layer, the convective zone. The tachocline is an environment of extreme contrast, where the relative uniformity of the radiative zone meets the boiling, bubbling convective zone. The strange conditions in this extremely thin layer likely plays a key role in the solar dynamo that generates the Sun's magnetic field. The tachocline is thought to twist and amplify the magnetic field, shaping the sunspots and solar flares that define the star's surface. Zipping through the thin tachocline, our photon arrives at the convective zone, stretching out from about 70% of the Sun's radius to just beneath the visible surface, the photosphere. The temperatures have dropped to below 2 million degrees Celsius. Now, the Sun's plasma is no longer dense enough to effectively transfer energy by radiation. Instead, the plasma becomes unstable and begins to move in massive convection currents, much like boiling water in a pot. Hot plasma rises towards the surface in large cells called granules. These granules, with diameters of thousands of kilometers, surge upward under their power of buoyancy at speeds of hundreds of meters per second, like a beach ball that you force below the water, rushing to the surface as it squirms from under you. The force required to move this volume of matter against the Sun's gravity is astonishing. Imagine the force of 10 billion hurricanes, and you'd be just starting to get close to the energy necessary. This convective process moves energy much more efficiently than the radiative zone, creating turbulent, rolling waves of plasma that churn vigorously. I've explained these convection cells and the beautiful hypnotic patterns they create on the Sun's surface in a lot of detail in this previous video. This is a significant change in how energy is transported. While photons still interact with particles, the primary mechanism of energy transfer in the convective zone is no longer the random absorption and re-emission between particles, known as radiative diffusion, but rather the movement of hot plasma rising and cooler plasma sinking. This convection motion carries the energy outward more efficiently than in the radiative zone. Upon reaching the top of the convective zone, the photon is carried to the photosphere, the Sun's visible surface. Temperatures have now cooled to about 5,500 degrees Celsius, and the plasma has thinned enough for photons to escape without being constantly reabsorbed. It is from this thin, roughly 500 kilometer deep layer that the light we see from the Sun is emitted. Above them lies only the Sun's corona, which is itself a fascinating environment, but only around a billionth of the density of the photosphere, and therefore not much of an obstacle to our photon. It is incredible that an object like the Sun, that many refer to as a ball of gas, can have such a sharp boundary. But the photosphere is where our photon finally breaks free, traveling at the speed of light and beginning its journey across the vastness of space. Our neutrino friend that was created at the same time? It's long out of the Milky Way by now. Since settling into its stable main sequence phase, nuclear fusion has altered the strength of the Sun's layers, gradually increasing its brightness over billions of years. This is because the fusion process inevitably leads to changes in the composition, density, and temperature of the Sun's core, which in turn affects the overall behavior and the future of our star. As hydrogen fuses into helium, hydrogen gradually depletes in the core, and helium ash begins to build up. Unlike hydrogen, which readily undergoes fusion at the Sun's current core temperatures, helium requires much higher temperatures to fuse. As the abundance of helium increases, the core becomes denser. Helium nuclei are more massive than hydrogen nuclei, and as more helium collects in the core, the overall density increases. At the same time, because helium is not fusing and creating energy, it does not contribute to the outward radiation pressure that counterbalances the Sun's immense gravitational pull. The result is that gravity will begin to dominate, causing the core to contract further. To prevent collapse under its own gravity, the Sun must increase its core temperature as helium builds up. The hotter core turns up the dial on hydrogen fusion because nuclear fusion rates are extremely sensitive to changes in temperature. This increase in fusion releases more energy, which results in a brighter star and temporarily restores the balance between gravity and radiation pressure. Through this process, the Sun's energy output has increased by about 30% over its lifetime, and this trend will continue for billions of years as long as hydrogen fusion dominates in the core. In the radiative zone, the layers have grown hotter and more opaque. The rising temperature of the core means more energetic photons are produced, which are more prone to interacting with the surrounding plasma and pinballing around. As a result, this zone has become less efficient at radiating energy outward, trapping photons for longer before they can continue their escape. The convective zone has also expanded slightly over time due to the increased energy production. As the Sun continues to burn through its hydrogen fuel over the next 5 billion years, its core will eventually be left overburdened with inert helium that can no longer sustain fusion under its own pressure. When this happens, the Sun will evolve into a red giant, dramatically expanding and engulfing its inner planets, including Mercury and Venus and possibly the Earth. In this phase, the core will contract and heat up until it ignites in a helium flash, starting the fusion of helium into heavier elements like carbon and oxygen, yet again swinging the pendulum between the relentless gravitational hammering and the resisting forces of energy from the core. This process will create new layers and cause the Sun to swell even further before shedding its outer layers to form a ghostly remnant, a planetary nebula. The core that remains will cool and fade, becoming a white dwarf, a dense, Earth-sized ember of a once raging fire. This transformation from a stable star to a red giant and eventually a white dwarf is a remarkable and complex process with many fascinating details, which we will no doubt explore in a future video. But ending our journey from the depths of the Sun's ancient past to its modern interior, let's return to that quiet hill where we began, watching the colors of sunrise. I hope the next sunrise you see becomes that little bit more special. I hope the pink and orange photons, scattered for one final time on the molecules of Earth's atmosphere before streaming through your pupils, will make you think of the incredible voyage they have endured, beginning with the collapse of a colossal cosmic cloud into an element-building furnace, struggling for hundreds of thousands of years through a melting pot of plasma to gift you with this beautiful scene. I hope this exploration has deepened your appreciation for that daily miracle we often take for granted. And there's still so much more to uncover about our closest star, from the formations it will undergo to the profound impacts it will have on our solar system's future. Thank you for joining me on this journey through space and time. If you found this journey as enlightening as our host Star, please give the video a like and fuse it with your own thoughts down in the comments below. Thanks for watching. I'm going to pull back the curtain a little here. Making videos about space is something I love, but it's also something I can't really do on my own. Don't be too surprised when you hear this, but I didn't go out and film all the footage I used in this video. Instead, when I'm not using space agency footage directly, I often turn to a stock media subscription service called Storyblocks, which has over 1 million 4K and HD assets of footage, templates, music, and more. So it was really convenient for me when Storyblocks asked to be the sponsor of today's video, because I can now just tell you about a service I'm already using. You just saw an example of the kind of thing it can make. With one predictable subscription cost, I can download as many high quality assets from Storyblocks as I like, which means I don't have to worry about wasting money for an asset I ultimately don't use. I also love that they have a plugin for Premiere and After Effects. By clicking on the top left here, I can search for videos that I want and it downloads into the folder I want and imports straight into the project. It saves a lot of time. But the best thing is that it's all royalty free. I've been burned by assets before that I thought I could use, only to have someone claim I'd breached copyright, demonetizing my video. I probably should have just used Storyblocks. If you're a content creator and need high quality stock footage or transitions, scan my QR code or click on the link storyblocks.com/Astrum in the description below. Thanks for watching. I was honestly blown away by all the incredibly kind comments and messages you've sent me, and by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 patron member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.